Hello and welcome to the November webinar from the IEA Clean Coal Centre. My name is Deborah Adams and I'm Studies Manager here. Our monthly webinars are based on our technical reports, which you can download from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after one-off registration. Please visit our website for details. Okay, the subject for today's webinar is the operating ratio and cost of coal power generation. The report on this topic is still out in draft for peer review and will be published soon. If you have any questions during the talk, please use the Ask a Question box at the top of your screen. Add your email address as well so that I can send you a fuller answer if we run out of time. Now, we've got a slight technical hitch, and then I'm passing you over to my colleague, Hermione Nalbandian-Sugden, who is going to give the presentation. One moment.
Debbie's trying to fix a problem that I created. I do apologize. I turned something off unknowingly. Okay. All right. We're back on. As long as I can see it, I can't see the bottom. Okay. I'll start anyway. First of all, thanks, Deborah, and good afternoon, everyone. As Deborah said, I shall be talking to you today about my latest review on operating ratio and cost of coal power generation. At the moment, the review is out in draft. It will be published and available on our website next month. The deadline for comments on the content of the draft is the 22nd of November, so if you have any comments, please email those to me as soon as possible and I will incorporate them if I receive them in time. I will begin with a brief introduction on the current status of coal in power generation. Then I shall discuss the operating ratios of some of the currently largest power generating companies globally. I will then move on to the costs of coal power generation, especially when operating in peak load, which will involve talking briefly about flexibility issues in coal power plants that were built mainly to operate in baseload but have had to modify their operations with the drive towards the greater utilization of renewable energy and, of course, distributed generation as well. And I shall finish with what the future looks like for coal at this time. To begin with, coal, as you know, has been the cornerstone fuel of the global energy system since the Industrial Revolution. Recent data shows that coal continues to be the first source, or choice if you like, in the power generation mix, as you can see in this slide. Although coal consumption has declined in some parts of the world, in recent years it increased in others. The report discusses some of the factors that will impact power generation with coal, including subsidies and distributed generation. I mentioned that before. By distributed generation, I mean the use of small-scale technologies to produce electricity close to the end user of the power. Now, the increasing use of renewable energy is already impacting the cost and utilization of coal power generation. But I must point out here that unlike the dispatchable sources of electricity, such as coal-fired power plants, non-dispatchable technologies such as wind and solar power provide a variable output to the grid that is not sufficiently reliable energy to be considered as capacity. Currently, renewables cannot be relied upon to meet the peak energy demand, under certain weather conditions, of course. For example, no sun or no wind. On top of all that, New rules for fossil fuel subsidy for energy markets have been adopted and will come into force in January 2017. These rules dictate official support for coal-fired power plants, including restrictions on official export credits for the least efficient coal-fired power stations. Next, I want to explain what I mean by operating ratios. Operating ratios, in the context of the review, are a representation of revenue and expense categories found on a typical financial profit and loss statement. They're presented as a ratio or a percentage value. In this report, it's percentage value throughout. The revenue ratios are a percent of total revenue, and expense ratios are also a percent of total revenue. As such, revenue ratios total 100%. Expense ratios may or may not. Expense ratios totaling less than 100% denote an operating surplus, that is profit. Those totaling more than 100% denote an operating deficit, i.e. loss. In the case of a deficit, a power company would either draw on its reserves or carry the deficit as debt into the next fiscal year. To put it simply, the operating ratio, given in percentage terms, as I said throughout the review, represents power generation operating expenses to total revenue. To clarify further, operating ratio in power generation is a ratio that shows the efficiency of a power generating company's management by comparing operating expenses to the net sales, or as I said before, net revenue. Meaning, the smaller the operating ratio, the greater margin an organization has to make a profit. Conversely, the greater the operating ratio, the lower the margin to generate a profit. Operating ratio calculations were carried out in the review on the profiles of 10 of the world's biggest power companies in 2014. The information basically was based on calculations of net market capitalization, assets, sales, and profit, as well as two major power generating companies in Asia. The companies were EDF, Enel, Uniper of E.ON, Iberdrola, Duke Energy, Exelon, Southern Company, NextEra Energy, Dominion Resources, SSE, Datang Power, and NTPC Limited. I'm sure quite a few of you would know that some of these companies are not involved in coal power generation, but the review was looking at the largest power generating companies, whether it was renewable or coal or fossil fuel based. Now, the operating ratios were calculated in the review from these companies' annual reports that are available in the public domain and were for the year 2015. The exercise was undertaken simply to indicate the year-on-year operational efficiency of these companies and to show where the operating ratio improved and or deteriorated. I have repeatedly stated in the review, and I will say it here, the operating ratios must not be compared between the different companies, as the information provided in the consolidated financial statements for each company differs from one power supplier to another, in that there is no breakdown of exact operating costs, especially where it isn't even clear whether staff or personnel costs were included or not. I'm not going to present to you in detail the operating ratios calculated for each and every company in the review. For that, you will have to see the report itself. Briefly, and in my opinion, an operating ratio of 75% or thereabouts may be considered desirable, as it indicates a company's ability to generate funds from the company operations and therefore produce revenue for future development and increased capacity. Within operational costs, there are many factors that impact the operational efficiency of a power generating business. These include cost of fuel, staff or personnel, as I said, operation and maintenance, and depreciation and amortisation. The higher these factors are, the higher the operating ratio is, and the lower the operational efficiency. Within a power plant, operations are impacted by many factors, including, for example, plant load factor, which is the ratio of the total kilowatt hour actually generated and sold to the total kilowatt hour which the plant can generate if and when it is run at full load. Another indicator is the overall availability factor, considered by some as a better index for comparing plant performance. I won't go into that here. As I said, the report will discuss that in detail. All in all, in order to achieve the desired operating ratios, that is maximum operational efficiency, within a plant or a power generating company, management as well as operational efforts are necessary to identify and resolve the problems in the various loss areas by taking the appropriate actions to maximize the power generation and minimize the loss. As I said before, the information given in the review on company operating ratios is based on annual reports, which vary in their presentation of revenue and operating expenses. And again, as I said, as such, comparison must not be made between different companies' operating ratios. However, a company management team may and should analyze operating ratios for a number of reasons. For example, to assess the operational efficiency and performance of the company over time, to allow a comparative study of operational efficiency at different times, and to highlight the position of the company with regard to revenue and operational expenses, which impact profitability and future investment. In simple terms, operating ratios data allows a company to compare its operational performance over different times, analyze the said data, and take the necessary steps in order to maintain as good an operational performance as possible, and as such, as low an operating ratio as possible. Moving on, determining the cost per unit of production of electrical energy, that is the 1 kilowatt hour, is known as the economics of power generation. Demand for electricity at a moderate rate is a driving force for the development and construction of power generating facilities that produce electricity at an acceptable rate to consumers. Terms often used in the subject of economics include interest and depreciation. Constructing a power station involves investing a large capital in the project. This is generally borrowed from banks or other financial institutions, and the plant owner has to pay an annual interest on the borrowed amount. As such, when calculating the cost of production of electricity in a facility, the interest payable on the capital investment must be included. The rate of interest depends on market conditions, among other factors, and has varied in the past between 4 and 8% per annum. Depreciation refers to the decrease in value of the power plant equipment and building due to continuous operation. If the power station equipment were permanent, then interest on the capital investment would be the only cost to be incurred. However, although a power station has a useful life ranging from sometimes 50 to 60 years, from the time the power station is constructed, its equipment steadily deteriorates due to wear and tear, resulting in a gradual reduction in the value of the plant, just like a car. As soon as you purchase it, it starts losing value. This reduction in the value of the facility year on year is known as the annual depreciation. Due to depreciation, a plant has to be replaced by a new one after its useful life ends. Therefore, theoretically, suitable amounts of income must be set aside annually, the so-called depreciation charge, in order that by the time the plant retires, the collected amount, by way of depreciation, equals the cost of a replacement facility. So, it is important that while determining the cost of production, annual depreciation charges be included. There are 3 commonly used methods for determining the annual depreciation charge. These are the straight line method, the diminishing value method, and the sinking fund method. I won't discuss those here, but please read the report if you would like to know more about these methods. Now, all costs faced by any company can be broken into 2 categories: fixed costs and variable costs. The fixed costs of power generation are essentially the cost of building the plant, mainly capital and land costs. The capital cost of building a power plant is regional and depends on the labor and regulatory costs, which include obtaining site permits, environmental risk assessments and approvals, and so on and so forth. Constructing a coal-fired power plant is a costly and a lengthy process in which, today, the costs of mitigating environmental impacts play a major role in the decision-making. Components of the variable costs are mainly fuel and operational maintenance costs. Variable costs depend on how much electricity the plant generates and sells. The operating cost required to produce each megawatt hour of electric energy is referred to as the marginal cost. Fuel costs dominate the total cost of operation for coal-fired power plants. For example, a 100 megawatt power station operating at 50% load factor may burn about 20,000 tons of coal per month and produce ash to the tune of 10 to 15% of the fired coal. That's about 2,000 to 3,000 tons of ash. In fact, in a power station, about 50 to 60% of the total operating costs can consist of coal purchasing and handling. Basically, the fuel, labor, and maintenance costs dominate the total operating costs. In general, power generating facilities face a trade-off between capital and operating costs. Plants that have higher capital costs tend to have lower operating costs. The operation and maintenance costs of power generation fall within variable costs, but have their own fixed and variable components. Fixed operation and maintenance costs consist primarily of plant operating labor and regular maintenance work. Variable operation and maintenance costs are due mainly to the fuel cost. Irregular maintenance work and to a continuous maintenance, variable operation maintenance costs are due mainly to the fuel costs, irregular maintenance work, and to a continuous maintenance contract that includes periodic inspection, replacement, repair of system components, and consumable. Disposal of residuals, as well as auxiliary materials such as water, lubricants, and fuel additives. Now, two fundamental indicators are used for cost comparison, in the electricity sector: capital cost and the levelized cost of electricity, also known as the LCOE. The levelized cost of electricity is a life cycle cost analysis of a power plant that uses assumptions about the future value of money to convert all future costs and revenues into current prices. What I mean by that is that the trade-off between capital and operating costs of different technologies makes comparing the overall costs of different power plants somewhat difficult. The levelized cost of electricity represents the per kilowatt hour cost of building and operating a generating plant over an assumed financial life and duty cycle. Key inputs to calculating the levelized cost of electricity include both fixed and variable costs, financing costs, and an assumed utilization rate for each plant type. The importance of the factors varies among the technologies. The levelized cost of electricity changes in rough proportion to the estimated capital cost of generation capacity. For technologies with significant fuel costs, such as coal, both fuel costs and overnight cost estimates affect the levelized cost of electricity significantly. Overnight cost is a terminology used frequently to describe power plants. It's also the cost of constructing a project if no interest was incurred during construction, as if the project was completed overnight. The unit of measure typically used when citing the overnight cost of a power plant is dollar per kilowatt. The availability of incentives such as tax credits can also impact the calculation of the levelized cost of electricity. However, please keep in mind that as with any projection, there's uncertainty about all of these factors, and their values can vary regionally and across time as technologies evolve and fuel prices change. This slide shows you the capital, operating, and the levelized costs of electricity in selected countries. The extremely low capital costs in China make it the cheapest country in which to generate power from coal. Coal plant capital costs are approximately $0.66 million per megawatt, which is roughly 80% below the global average. When coupled with imported fuel costs, for example from Australia, the levelized cost of electricity for Chinese coal are as low as $35 per megawatt hour, less than half the estimated levelized cost of electricity for a comparable new-built plant in Western Europe or the United States. These costs can be even lower when the cheaper, locally mined coal is used, which is the case for coal plants close to the mining centers, such as in Inner Mongolia. This figure shows you the effect of operating hours of a plant on the cost of electricity production. A report on the development of the global and European electricity demand considered that electricity generation costs will double if a power plant unit that is designed for baseload, with about 6,000 estimated full load hours, is operated for about 2,000 hours. If that plant's operating hours are cut further by another 1,000 hours, generation costs can increase by a factor of 4, as you can see in the figure. This has a particularly negative impact on highly efficient new power plant uptake and siting, because these are burdened by a high share of fixed costs, mainly made up of capital, staff and maintenance costs. In Europe, to secure reliable supply, the mechanisms of the European energy market need to be reshaped in order to realize new power plant projects, that is, to have a dispatchable and disposable backup capacity. I'm going to briefly touch on CO2 here, carbon capture and storage. Carbon capture technologies are associated with significant energetic and economic penalties, reducing power plant efficiency by around 10% points and increasing the cost of electricity production by up to 80%. Also, carbon capture and storage is not commercially viable yet due to the high costs, both, as I said, in monetary and power consumption terms, and remains mostly in the demonstration stage. The availability of carbon capture and storage technology will be primarily determined by technological progress. Progress in improving the technologies depends on the fuel and CO2 pricing, greenhouse gas policies, and uptake of renewable energy sources. Analysis indicates that CO2 emission pricing needs to reach $30 per ton CO2 in order for plants equipped with carbon capture technology to be competitive with coal-fired power plants without carbon capture and storage. In Europe, calculations suggest that carbon capture and storage cannot be profitable at carbon prices below 70 euros per ton CO2, and as well as favorable conditions regarding fuel prices and full load operation. In 2012, when prices were lower than 10 euros per ton CO2, carbon capture and storage could not be considered competitive at the then state of technology development. As recent as August 2016, specifically on the 10th, the price was 4.8 euros per ton CO2, far below the 30 euros per ton CO2 analysts consider the minimum price required for driving emissions reductions and low carbon investment. Estimates for carbon capture and storage market deployment, at least as a retrofit technology, range from an optimistic 2020 to as late as 2070. Given the current state of the technology and numerous analyses, 2030 is considered a realistic time frame for wide-scale commercial application of carbon capture and storage technologies. Now, historically, coal-fired power plants were designed to run most efficiently and cost-effectively when providing baseload. By that I mean running at a steady and continuous rate. Renewable energy systems, such as wind and solar, as I mentioned before, vary with weather conditions and are therefore much more sporadic in their energy output. However, the energy from renewable sources is currently prioritized for input into the grid in many countries, and the trend is expected to continue and spread. This means that coal-fired plants must now provide more flexible output to keep the available energy in the network at the required level. And as you saw, there's an impact of running a plant at reduced hours on the total cost of electricity production. You may have also observed that the cost of plant maintenance increases. The increase in maintenance cost is due to cycling, which is a range of operations in which a plant's output changes, including starting up and shutting down, ramping up and down, and operating at part load. In other words, less than full output. Ramping results in output that varies between full and minimum levels in order to follow changes in generation demand. Now, cycling a coal-fired plant puts a strain on the boiler and increases the risk of operation and maintenance problems. The conversion of baseload plants to cycling units and the extension of intervals between scheduled outages is changing power plant operations as well as maintenance programs. The impact of cycling and key steps for improving flexible operations in coal-fired plants is shown in this slide. And of course, all that comes at a cost. Operational changes due to improving or increasing its flexibility of a traditional and/or modern coal-fired power plant include faster load ramps, more startups, more frequent load changes, more frequent minimum load operation, and reserve shutdown. The impacts of such operational changes on the plant operation maintenance include increased fuel costs, increased number of thermal cycles, as I said, the cycling, reduced plant efficiency, maintaining cycle chemistry, increased corrosion, increased component wear and tear, and impact on downstream emissions control technology devices. The flexibility capabilities of modern advanced coal-fired power plants include startup times of 1 to 4 hours, down from 2 to 6 hours, and minimum loads reduction capability from 40% down to 25% and even lower. In addition, if indirect firing is used and improved, primary frequency control times can go from 2 to 5% within 30 seconds to 10% within 10 seconds. The modern state-of-the-art supercritical and ultra-supercritical coal-fired power generating plants can achieve what they are built or designed for, but are significantly more expensive than currently the more widespread subcritical systems, which, without modifications, would struggle with having to operate profitably and efficiently in flexible modes. Cycling, as I said previously, is a range of operations in which a plant's output changes, including starting up and shutting down. Where plant shutdown occurs, the startup conditions, hot, warm, or cold, will depend on how long the plant is offline. A cold start is when a power plant has been shut down for more than 50 hours. A warm start is when a power plant has been turned off from just over 8 hours and less than 50 hours. And a hot start is when a power plant has been switched off within 8 hours of the next startup. Hot starts are a characteristic of power plants running in a daily cycling mode, which are shut down overnight and start generation in the morning. The colder the plant before startup, the greater the increased risk of damage to the plant. However, the damage caused by this cycling may not be immediately apparent and can take several years before manifestation. Studies suggest that it can take between 1 and 7 years for evident increases in the failure rate following the switch from baseload operation to cycling operation. This slide shows a typical cycling cost breakdown for a large coal-fired unit in the United States. As you can see, operation and maintenance costs go up in all three scenarios, but are more pronounced with cold startup operations. Cycling baseload units, which are not designed for flexible operation modes, can result in increased or more frequent component failures and sometimes longer duration unplanned or forced outages. As you can see in this chart, a forced outage is, as I said, an unplanned component failure or other condition that requires the unit to be removed from service immediately or within a very specific time frame in order for the necessary work to be carried out so that the plant can start operating safely again. The equivalent forced outage rate is the terminology used to express the hours of unit failure, that is, the unplanned outage hours and equivalent unplanned derated hours, given as a percentage of the total hours of the availability of the unit. The lower the equivalent forced outage rate, the better the performance of the unit. The equivalent forced outage rate is also considered a measure of a plant's unreliability. So, the impact of cycling on plant outages and increased maintenance requirements can be significant. In addition, the increasing competition in the electricity market has affected staffing levels. whether due to the cost of labor or a drive to greater efficiency. As a result, plant operators began outsourcing some or all of their plant maintenance and materials management, more so in the USA and Europe, for example, compared to some countries in Asia. Where some or all operational maintenance services are outsourced, it is important that the service contracts define all operational and maintenance activities that address efficient plant operation, including tracking operating changes, improvements, deficiencies over time, and keeping a record of activities to detect and troubleshoot maintenance and operational problems. The records would provide staff and management with critical data for comparing historical and current conditions in the plant equipment, components, and performance. Taking a tracking preventative maintenance approach would also assist plant personnel in locating recurring problems, understand when equipment performance is degrading, and ensure that the operation maintenance contractor performs the tasks according to the contract. This slide summarizes findings based on using an analytical hierarchy process as a modeling tool. An analytical hierarchy process uses a hierarchical structure to sort both tangible and intangible criteria in operation maintenance based on their relative importance. The process makes pairwise comparisons between each criterion. Or in simpler terms, the modeling is based on logical analysis of all key criteria. Now the figure shows the tendency for a large utility would be, as expected, to prefer internal supply or minimal outsourcing, whereas an independent power producer with little experience would be expected to favor a more comprehensive level of outsourcing. However, with, as I said before, the increasing competition in the 21st century in the electricity market, some utilities have opted to outsource more, and in some cases all of their maintenance requirements, with increasing focus on asset management and the generation and sale of energy. Outsourcing power plant equipment maintenance to third parties is on the increase. The increasing fuel costs combined with the newly adopted strict regulatory emission standards as well as tariff-based bidding are exerting pressure on independent power producers in India. So I'm using that as an example. For example, there's focus on improving operational efficiency there by increasing plant availability, reducing operational costs, increasing plant load factor, and becoming overall more competitive, especially when it comes to cost. This has resulted in evaluating operational maintenance options, including outsourcing. As discussed previously, inadequate operational maintenance can have multiple impacts on performance, including reducing plant availability, causing higher station heat rate, higher auxiliary power consumption, and subsequently reduced profit. This slide shows the impact of a poor operational maintenance strategy on a project's internal rate of return. The example is based on a 1,300 megawatt coal-fired power plant in India. As you know, the internal rate of return can be defined as the rate of return that makes the net present value of all cash flows equal to zero. This figure shows that a 5% decrease in availability can reduce project returns by over 17%, and a 1% increase in auxiliary power consumption can potentially reduce a project's rate of return by 6%. In a worst-case scenario, poor operational maintenance can lead to more than 27% reduction in a project's return. However, with the limited availability of a skilled labor force and difficulties in attracting and retaining knowledge and talent at remote locations, independent power producers can face serious operational maintenance-related challenges. Because of that, outsourcing of operation maintenance has become a growing trend. However, it is essential to understand the core competencies within the independent power producer and evaluate different outsourcing options before deciding upon an operation maintenance strategy. The four predominant types of operation maintenance strategies or models followed by independent power producers in India are discussed in the review. Please read the report for advantages and disadvantages of outsourcing operation maintenance services and the necessity of evaluating those, as well as other parameters such as personnel and costs prior to the outsourcing. I want to briefly here, as I did in the review, discuss the role of I seem to have a little problem here. Before I will go back to that slide, I think I've missed a slide. Hold on. I will continue. I want to briefly here, as I did in the review, discuss the role of automation in a coal-fired power plant. Today, many, especially the modern coal-fired power generating stations, rely on a complex network of sensors, actuators, digital controllers, and supervisory computers to operate and coordinate each of the plant subsystems. In a modern system, numerous feedback control loops serve to monitor the plant processes and perform the appropriate control actions, aiming to maintain optimum operating conditions, regardless of system disturbances such as changes in coal quality, for example, or load demand. A digitalized analytical system has a greater capability to respond to the highly interrelated parameters of a power plant and enables closer control and reaction to changes by having immediate access to the data from the complex system components. The benefits of digitization in coal-fired plants are purported to include increased reliability and availability, leading to reduced emissions and increased profitability. This slide shows how a marginal improvement of 1% in performance and efficiency in coal-fired power plants in India can have a potential impact of $5 billion over a 30-year lifespan. To calculate the potential benefits, the assumption is that the average plant heat rate for a typical 200 megawatt coal-fired plant in India is about 2,400 kilocalories per kilowatt hour. Assuming the same heat rate for India's total installed capacity of approximately 185 gigawatts, a 1% reduction in heat rate would have a significant impact on savings, as you can see in this slide. So, what is the future for coal, as seen today? Based on the forecasts shown in this figure, come to which most projections and forecasts show practically the same thing, coal will continue to have the largest share in energy production in 2030, although the shares of both coal and gas will decline in the global fuel mix, while the share of renewables will rise, is expected to rise at least to more than 40% by 2030. The changes in the global fuel mix is driven by mainly environmental pressures, especially climate change, and the utilization, of course, of more flexible generating systems. Global coal consumption declined in 2014 and more so in 2015. However, in power generation and between 2010 and 2015, coal-fired power plants were constructed in 33 countries, but only 8 of those countries added a capacity exceeding 2 gigawatts. I'll list the country anyway to just give you an idea. The countries were China, India, USA, Indonesia, Germany, Vietnam, Turkey, and Chile. Those were the countries that had built more than coal-fired plants with a capacity greater than 2 gigawatts. China and India alone accounted for 85% of all new coal-fired capacity. This figure illustrates the regional distribution of new coal-fired power capacity built between 2010 and 2015, showing that over 90% has been in Asia. For plants currently under construction and planned for the future, the trend seems to continue, in that more coal-fired power generation facilities are planned in Asia than any other region of the world, as you can see in this figure. The report goes on to give a concise overview based on different regions of the current status and what's happening and planned with regard to coal-fired power generation. Finally, the consensus is that the likelihood of a significant amount of new coal-powered generation coming online in Europe and North America is low. In 2013, in a report on world energy perspectives and cost of energy technologies, the World Energy Council assumed a 10% cost of equity for a base hurdle rate in their study. But indications were that actual hurdle rate demanded by investors to agree to supply capital for a new build coal-fired plant may be in the order of 18% or even higher. In some regions, such as Europe, new coal-fired plants would be subject to an uncertain future carbon price, which is the main reason why investors consider these plants risky. However, in some parts of Europe, new coal plants continue to come online, for example in Germany, where the nuclear ban and other market-specific factors are likely to necessitate new additions for the next few years. Coal-based power generation continues growing in parts of South America, but China, India, and Southeast Asia are the main markets for new coal development. Many of the conventional existing coal-fired power plants today were constructed prior to the expansion targets for and adoption of intermittent wind and photovoltaic power. In many of these plants, measures to allow greater flexibility have been implemented subsequently, so that power plants can meet increased requirements for market load adjustments. As a result, many baseload power plants have been modified or are taking the necessary steps to allow for flexible operation at reasonable cost. Control of these costs can play a significant role in improving operating ratios and maintaining greater operational efficiency in power generating companies. In conclusion, despite the growth in renewable energy, fossil fuel generation capacity will continue to grow in absolute terms in all scenarios. Although its relative contribution is forecast to fall from 67% in 2012 to 40 to 45% by 2030. However, the growth in coal capacity in the long term is expected to slow significantly, and especially so with the imposition of effective and robust carbon pricing schemes due to environmental concerns, especially climate change. Then again, there is a big question hanging everywhere right now, and this is a bit political, but will Trump's presidency topple international effort on climate change? Now, Trump becoming president of the USA does not alter the situation for the Paris Climate Agreement. There is what we are assured by the negotiators. The reason given is that the agreement, which was ratified by the USA on the 4th of November, has an effective lock-in period for 4 years, which includes a year's notice period. So theoretically speaking, according to the negotiators, President Trump would have to win a second term in order to officially pull out of the 2015 Paris Agreement. However, no one knows it yet what's going to happen, and all everyone can do right now is wait and see.
Lovely. Thank you very much, Hermione. I'm afraid I don't think we've got time for any questions today, but you can see Hermione's email at the top of the last slide. So if you do have any comments, please email Hermione directly. Just quickly, I'd like to say that the next webinar from the IEA Clean Coal Centre is an update on public outreach approaches to carbon capture and storage. So I'm sure that'll be another interesting presentation, and that'll be presented by Toby Lockwood on Wednesday the 19th of December. I think it's the 19th, might be the 14th. Anyhow, thank you very much for listening, and goodbye.